All right, let's talk about ensembling, which is currently pretty much the state of the art of what you can do in predictive modeling. Not just use one model, but why not use basically every model that we've tried out? So, one thing we know about the no free lunch theorem is that there's not going to be one best model for every situation out there. The no free lunch theorem has guaranteed us that we do need to do our work and try out a bunch of different models and see which one happens to be doing the best for a particular situation. Now, each one of these problems or each one of these models that we've discussed, the nearest neighbors, partition model, naive Bayes, they've all approached the problem from a slightly different angle. And so each has learned something a little bit different about the relationship than each other. Depending on the specific form of the relationship, some have been more effective than others. But why not try to combine the predictions from all these approaches to get a more complete understanding of the relationships that we're studying? If each one of these models is learning something a little bit different about the relationships, it stands to reason that combining them together would improve the predictions upon any one of them individually. And so combining models' predictions is the basis of what we refer to as ensembling. And we're already kind of used to this. So back when we talked about bagging and random forests, we discussed this whole strength in numbers approach. The reason that random forest was building a whole bunch of different trees on slightly different versions of the training data, using random subsets of predictor variables each time it needed to add a new rule to the tree, was that each tree, when built that way, was as independent from each other as possible. And people have studied this and people have realized that when you look at the average of many guesses, well, the average of many guesses typically has less error than any one of those guesses in isolation, and that decrease in the error in the average is the largest when the guesses are independent, or at least correlated with each other as possible. Doing that bagging procedure with the random forest to construct each tree on a slightly different version of the data, selecting a different random subset of predictors each time a new rule is going to be added to one of those trees, ensures that the trees look as different as possible and are as uncorrelated as they possibly can be. That way, when we average together their guesses, we do get a performance increase. And so, even though when we've gone through and fit a lot of different models, each of those models' predictions are going to be somewhat correlated, there's still a decrease in the error when we use an average instead of an individual guess when that's the case. So that's what we're going to run off of. We're going to say, all right, well, each of these models we've looked at are looking at the problem from a slightly different angle. We could probably learn something from each one of these models, so we just need to combine them in an intelligent way. So, how do we come up with a strong ensemble of models? Well, the key is diversity. We want to make sure that the predictions that these models are making are as different as possible, essentially. They're really probing different aspects of the relationship. It's not going to make much sense to combine, say, a vanilla partition model and a random forest. Those procedures are very, very close to one another, not really approaching the problem from that much of a different angle. Logistic regression in random forest, well, that's quite different. Nearest neighbors, random forest, that's really different. Neural networks, nearest neighbors, also very different as well. We can see that, okay, combining some of these models that we've talked about might be a really good idea. So how do we combine them? Well, the simplest way would be to just, average together the predictions of your many different models. Have each model have a vote over what that individual's class is, or average together all the models' predictions for y, and call it a day. That's definitely one approach. A smarter approach would be to come up with a weighted sum for each of those models. So each of the models are outputting some sort of predictions. Some models are more accurate, more trustworthy than others, so they should probably have a higher weight than others. So we could come up with an intelligent weighting scheme to come up with a weighted sum of the predictions. There are other ways of doing it. Blending is an interesting way, where you might make, say, predictions from a random forest model, a nearest neighbor model, a logistic regression model, and use those predictions as predictor variables in a neural network model or some other type of model, support vector machine. The way that we're going to focus on combining predictions from different models is what's known as stacking. Basically, what we're going to do is we're going to treat the predictions of the different models as features, basically new x variables, that we're going to combine together into an overall model to help predict our value of y. So why should this work? Well, just think about, the real world. If you go out and interview for a job, you're going to be sitting down with a bunch of different people. They're going to ask you slightly different sets of questions, and they're going to assess your capability and your competence from slightly different angles. At the end of the day, all those interviewers get together, they talk about you, and they get a more holistic approach of whether or not you're suitable as an employee or not. And that's the same sort of thing that's going on with an ensembling. Each of these models are approaching the problem from a slightly different angle. They all have something to say. Let's let them all speak, but we'll give them more reliable voices a little bit more weight than others. Let's learn how we can ensemble. So here's the basic idea. What we're going to do is we're going to fit the logistic regression model. We'll fit the support vector machine, naive Bayes, boosted tree, nearest neighbor, everything that we know how to fit. And what we're going to use are those predictions as our predictor variables in our ensemble model. So for instance, if we're going to use a neural network to do the ensembling, we might let the predictions from these 5 different models be our input layer. We'll come up with maybe 4 different weighted sums of those predictions to transform them through the activation function, only to reweight, retransform them again to come up with our final prediction. So we might come up with some nonlinear combination of the predictors, which could end up being stronger than any one model's predictions alone. And so this is why we use Carrot, because Carrot actually has a package that allows us to do this ensembling very effortlessly. So Carrot knows how to play with a lot of different models. If you get model info for on Carrot, it'll spit out all of the models that it knows about. A lot are really, really close to each other. There's a lot of different flavors of the technique called AdaBoost, for instance. Some models do classification, some models do regression, some do both. You can get what type of model is good for what by running the get model info as well. And you can even look at some of the code for how each of these models are set up if you want to venture out and try a new type of model that we haven't even discussed. So anyway, let's talk a little bit more about stacking. That's the way that we're going to try to ensemble the models. Basically use the predictions of each model as new predictor variables, new X variables, to put in as inputs to a new model here. We need to be very careful about how we set this up. So here's what we're not going to do. We're not going to fit to the each model to the entirety of the training data, save its predictions, and use those as the X variables to basically repredict Y in a linear regression or support vector machine, etc. So why do we not do this? Why is this a bad idea? Well, if we do this, we're basically reusing the training data. We're using the training data twice for 2 different tasks. First, trying to figure out what the random forest looks like, what the logistic regression looks like. And then we're using it again to figure out, okay, well, how should we weight or combine these predictions together to come up with our best estimate of Y? If we double dip like that, if we reuse the training data for 2 separate tasks, that's a surefire recipe for coming up with an overfit model. Specifically, the way that this happens is with this term called response leakage. Basically, if we were to fit a model onto the entirety of the training data and use its predictions as new variables, those new variables would have hard-coded into them what the Y values of the individuals in the training data were. Because that's how all these models were set to begin with. It's what the random forest looks like. It's what the regression looks like. It was using information about that individual's value of Y to come up with those predictions. And so it doesn't make any sense to use those predictions as is as new predictors because it's hard-coded some of the information about Y. And we're not going to know what new individuals' values of Y are in the future, so that's a little bit shady. So instead what we're going to do is as we're estimating the generalization error of each one of the models to go in our ensemble, to get an idea of how trustworthy each are, during that k-fold cross-validation, we're going to use the predictions on the holdout fold to use as the new X variables when we develop the ensemble model. Now visually, what does that look like? Well, here's our visualization for four-fold cross-validation. In round 1, what's going to happen is that the model is fit using the first 3 folds for the training data, and it makes predictions on that pseudo holdout sample. This is how we're estimating that generalization error that we've been doing all along. Now what we're going to do for the ensemble model is to save the predictions on the holdout sample to use as the new variable, or new predictor variable, that goes into the ensemble. That way, these predictions aren't using any information about what the Y variable for these individuals are. when it's constructing it. And then when we go through all 4 folds, we basically, piece by piece, kind of fill in what the values of that new predictor variable will be for each one of those models. Each one of those predictions won't have any response leakage because they don't have any information inherently about the Y value of those individuals. So once we have that, we're good to go. Now, stacking is a very sophisticated procedure. It doesn't improve your models a lot. You can, if you really want to squeeze out the last bit of predictive performance, well, stacking, ensembling is what you need to do. If you're going to want to win a Kaggle competition, you're going to have to fit a lot of different models. You're going to have to stack them. You're going to have to combine them in some way. It doesn't give you a huge performance increase over, say, the strongest component of the ensemble, but it does typically give an increase nevertheless. Now, it's very time consuming, etc. I'll have you work through it on a handout. It's not very good for, going through slide by slide or whatever, but it's a pretty easy process thanks to Carrot. So here's the disappointing thing. I've been saying that, okay, the state of the art is to fit a bunch of different models, make an ensemble out of them, squeeze the last bit of predictive performance out of your models. It doesn't usually give that big of an increase in performance, not a very large decrease in error. And that people find that pretty disappointing. So why isn't the case? Why doesn't it give a huge boost in performance? Well, it's because the predictions of the models in the ensemble, even though they approach the problem from different angles, still tend to be very highly correlated. It's when we average together a bunch of independent guesses where we get the biggest increase in accuracy or the biggest decrease in error. We tend to get a smaller decrease when we average together correlated guesses, and that's what's going on here. The models are all, pretty darn good. Their guesses are pretty correlated with one another, so we only see a pretty small decrease in the overall error of the ensemble. And on top of that, ensembling works best when you have lots and lots of data. I'm not even talking about the data sets that we've worked with this semester. Those are pretty small by comparison for the data sets where ensembling really has a chance to shine, where it's really able to squeeze out every little strength of the models going into it to perform the best. So ensembling will do it. We'll see a tiny performance increase. It's definitely the wave of the future, though. As data sets get bigger, as models get more sophisticated, ensembling is going to become more and more of a thing. So you can read more about the Carrot Ensemble package at this link here. You'll go through some examples on the activities and the homework, and that brings you up to the state of the art in predictive analytics. No one out there knows any more than you guys do at this point for coming up with the best predictive model.